Okay, wonderful. Thank you all so much for joining us. Today we are joined by our colleagues from the Space Telescope, and we'll have two talks about their activities. The first talk will be given by Dr. Susan Mullally. She's an expert in astronomical time series data collection and analysis. She's a mission scientist at the Data Science Mission Office. Previously, she worked in the MAST, she will tell us about, as the lead for archiving the data from TESS mission and to improve the archive for the TESS and Kepler missions. She received her PhD in astronomy from University of North Carolina, Chapel Hill, and she has been studying the population of exoplanets in our galaxy and the details of the stellar evolution, worked to find and understand nuclei, for instance, of tidally distorted eccentric binary stars, knows as heartbeat stars, that I learned only when I was exploring this. And she will give us a talk about the MAST. So take it away, Susan.
Hi, everyone. Thank you for inviting me to tell you about the MAST. Yeah, I'm Susan Mullally. I'm currently the acting PI for MAST. Our Noble leader, Josh Peak, is on sabbatical right now, and I'm his deputy. I've been in this role for about 4 months now as deputy, and only been acting PI for a month. So this has actually been a great opportunity to get my head around everything we do here at MAST. And so I'm going to give you a bit of an overview of who we are at MAST and some of the things we do, and highlight some of the things we're thinking about. Mostly it's a chance to give you some fodder to ask me lots of questions about things that we are diving into and how we're trying to make our data more accessible here. So MAST is the Mikulski Archive for Space Telescopes, and it is run out of the Space Telescope Science Institute. Let's see if I can change slides. We have many missions. This isn't all of them. We are the home archive for the Hubble Space Telescope, as well as the James Webb Space Telescope. We are also operating the operating TESS, which is a time series photometry LSky time series mission. And we'll soon also have a piece of the Roman Space Telescope. But you can see we also are the archive for all sorts of legacy missions, including Kepler and K2, which are very similar to TESS, as well as ultraviolet missions like IUE and GALAX and FUSE. I'm sorry if I missed one of your favorite missions on here. We have data going back to the 1970s. This is approximately, for some of our popular missions, sort of what our data distribution looks like. So you can see on the y-axis is the demand, so how much data is downloaded from these particular set of data from a particular mission versus how much data volume it actually is in the archive at this time. This actually graph came from a couple of years ago, so it's a little old. So JWST wasn't even on there, so I stuck JWST in the middle just to give you a sense as to where it is. But you can see that in general, like missions like TESS, which are now moved because TESS has 2 more years of data, so it's now a couple hundred terabits. I'm sorry, this whole thing's in terabits. A couple hundred terabits of data now of just the mission data. We actually have other products as well, which are grouped in that high-level science product, HLSP, which I'll tell you a little bit about as well. And then for some of our missions, we're serving to the wider astronomical community of more than a petabit of data. There are times when suddenly we have to serve lots and lots of data at once. That happened most recently with JWST back in July when we released the very first set of data. There was only something like 50, I don't know, 30, I think I have it on here, about 30 terabits of data in the archive, but we sent out 3 petabits of data in basically 1 month to hundreds of countries around the world. And a lot of that has become possible because of things like the cloud. So because we put the JWST data, that initial data release, into the cloud, more and more people were able to easily get at it. So we have lots of other data products. At MAST, there's kind of a few ways we're curating even more data. One comes from high-level science products. These are community contributed data products that complement and supplement what we already have at MAST. So frequently there are things where people take the data we have, like for Kepler, we might have had Or for tests is a great example where we have lots and lots of data of individual observations of stars or pixels, and they turn them into light curves, time series photometry, and deliver it to us. Or for HST, people will take lots of different imaging and create an enormous mosaic and then give it to us so other people can use it. We provide guidelines. We don't just take anything. We ask people to really put the data in a format that we can easily archive it and has good metadata for people to be able to use it later. And so we've provided guidelines for how to do that. In general, we're finding these high-level science products contributed by the community actually really lower the barrier to archival science because frequently they are very highly processed products that people can immediately just use to do science. So you don't have to understand the intricacies of the instruments and everything. You have something ready to use just to make a measurement. And you take all of these community contributed products together, it's as competitive in terms of popularity as one of MAST's flagship missions like HST. Just because I can't give an astronomy talk without showing a few pretty pictures, and this was my chance to put a couple in here. This is an example of a couple of the community contributed high-level HLSPs. What you have here on the right is JWST early release observations. So they created their own mosaic of these images, combined the filters, and did their own processing of the data. And so that processing got delivered to us, not as just through the mission pipeline, but as a high-level science product for people to use. So that there's the JWST ERO, but then we also have things that like here's a NIRSPECT and MIRI IFU spectroscopy called a collection called templates, for instance. And this frequently involves combining data from other missions as well, like HST and Spitzer and ALMA and JWST all working together in one product. I will get back to HLSPs when it comes to tests in a second as well. But in terms of other ways we have lots of collections is we also solicit collections from small missions. So for instance, NASA's have these Explorer missions and Pioneer funded balloons and small sat missions. And they are highly recommended that those data are archived at one of NASA's archives. So we are the UV optical IR archive, but there's also, the IR millimeter one out at URSA, and HESARC has more of the high energy data. And so we end up with lots of disparate collections in this way, but we welcome them and we fit them into our same framework for delivering and giving people access to these data, because it would be a shame if they were lost. And we really do take our job seriously in making sure these data are around for people to use in perpetuity. Most recently, this was done with the thin spear data. It's a UV imaging spectrograph that was launched in 2003. We actually went and got this data and made sure that it made it into the archive. So all of this is to say that what we do then here at MAST is that the idea is to maximize the scientific accessibility and productivity of astronomical data. We find that as we improve accessibility, we actually are increasing its productivity and we get more and more science papers out. And one thing we have noticed is that people who have fewer resources are more likely to do research with archival data. It's an easy place to come in and start doing astronomical research. We also find that MAST publications that are from not PI-led HST, I applied for this time kind of data, but from data that's in our archive and was freely available for people to use. If you look at the publication rate, as a function of time, which is the combination of all of our missions is in the blue line. And if you look at the dotted line, that's HST's publication rates. And you see in 2020, MAST's mission publications were as many as we got from HST. So MAST in itself is essentially a science generating machine without taking any new data. Well, there's always new data coming in. Maybe that was a little too extreme, sorry. So what are some of the ways we're enhancing productivity and accessibility? Some of the things we're working on. I will just I know everybody knows we have lots of GUI interfaces and an API so people can programmatically access our data. The prime way for MAST people to get our data in a multi-mission kind of perspective is our portal. If you haven't been there, this is what it looks like. It gives us an opportunity as well to do things like hook in quick looks so people don't have to, they can look at the data before they download it. They can do filters across many different missions if you're not really sure what you're looking for. But one of the things we've been working on most recently has been improving our mission-specific pages, because as you can imagine, when you have a large enough data set from one particular mission, you have specific terminology, certain deep kind of searches into that data set that you really want to get at. And so these are our specific mission search retrieval, and they all started as these PHP pages. Like this is an example from Kepler that's still live. So it has things like Kepler ID, that's the catalog that people come into with that thought process. You can search by quarter, which is a specific term used for Kepler, for instance, to get back exactly Kepler products. But we've been revamping this and trying to get it all into the same technology on the same sort of microservice layers. And so if you use Hubble at all, you'll notice we created a new beautiful page for Hubble. This is a specific mission search page that is tuned for Hubble. So it has, Hubble's instruments, Hubble's legacy instruments as well, and allows you to do deeper dives into the Hubble archive. This is all built on technology like Vue.js and Fast API. The whole thing was made to be faster even than what the portal is, so it runs really sleekly, and with an idea of really starting from the sense of user design and user experience. And so we're trying to move things into this for our search pages for individual missions, and then hopefully someday we'll be able to unite them back into a new central mission form. It's kind of the vision and we're trying to head towards, so that they all come together as one set. But since we have all these individual missions, we have to move them sort of one at a time. And so right now we have 4 of these new pages. They're trying to kind of do it across different types of missions. Classy is like a small, simple collection, where Ulysses has all sorts of complicated things. HST was the first flagship one to go. And now we're starting to work on a JWST one, will hopefully come out, and it's several months from now still. Okay, so that was one way that we go about trying to make data accessible to everyone. Another thing we really think about is ways we can give people, parts of data. Cutouts are really important to a lot of the missions we do, at least it's used especially for TESS and pan-stars. This was just to give you a sense of what TESS is like. TESS is a large, sorry, you're still there, right?
Yep.
Okay.
Yes.
Yeah, sorry, all your videos, something went blank, so I was worried. They're back. Okay, great. So TESS is an all-sky mission, and so for 1 month it stares at a piece of the sky, and these 16 CCDs read out that large swatch of sky, which is 24 by 96 degrees. So each pixel actually takes up 21 arc seconds. So imagine you're seeing there. But it does great photometry this way. But as you can imagine, you wouldn't want to have to work with all these individual full-framed images when you're interested in those 4 stars. And so one of the things we did was we made it easy to do cutouts across this time series, because TESS takes one of these observations every 200 seconds, right? And so you're not going to want to download these big FFIs if you really just want the time series of the pixels around your favorite star. And so we provide a service called TESScut to do this, which has both a graphical interface, which this little video shows you, as well as an API behind it. So you can, which has then been wrapped by other people's code to easily say, oh, okay, I want to do a search using TESScut on HP11, and that returns you just those pixels as a time series that you could then do photometry on to get out a light curve. And so this has really accelerated TESS's ability to produce science very quickly, because scientists themselves didn't have to have a whole archive of full-framed images around. They could easily do cutouts. And we've even now worked to move that service to work even faster into the cloud. And this meant we had to like stack all of the FFIs into one big data cube and then turn it so you could do efficient cuts just along that time axis. And so these are those high-level science products that essentially have come out from being able to use these kind of cutout services because they're interested in giving you a time series for individual stars, which the test mission itself was not delivering. So the community stepped up to do that for them. And a lot of these, that's what it is. And so most recently, I think it's the GSFC Illinois Light, they sent us 150 million light curves from those test data that we then are now responsible for archiving as well. Okay, so that was a lot about, particularly about just different ways we've gone about delivering data and making it easy to get at it. The other thing we think a lot about here at MAST is sort of lowering barriers. How do we get people the information they need in order to use those data effectively? Because one thing that does happen is that missions eventually end. And all that mission knowledge has to go somewhere. And that mission knowledge goes to us, MAST. For instance, I came from the Kepler mission, and there is no Kepler mission office anymore. And so anything you want to know about using the Kepler data is now here at MAST. And they're lucky that they have me. Sometimes questions then come through to me. But if you don't know a scientist who worked on that mission, then it can be very hard to feel comfortable enough to use that data. And what MAST wants to be sure is that we've left enough that the missions have left enough information behind that people can effectively use those data. And so we do things like, and Erik's going to talk about notebooks. I don't need to talk about notebooks, but one thing we're doing is curating notebooks with lots of information about how to use those data. But the other thing we'd like to do is integrate that those notebooks with a place that people can run code that we know works in order to get out great science. And so what has happened is in the process of moving data into the cloud, we've moved HST, Kepler, K2 tests, and we're moving more and more data into the cloud. It allows us this opportunity to allow people to do compute next to the data up on AWS. I know I put this diagram in here like I'm a platform developer and can tell you what this means. But essentially we are doing a Jupyter hub on a Kubernetes system. And so I know that I have some technical people in the crowd, so I'm giving this to you. But at the end of the day, what we actually have is people coming into our permanent platform, for instance, is Tyke to do time series data, where it's full already of notebooks that show you how to do time series data analysis on this Jupyter Hub platform. It's pre-installed with this software they are used to using. So we're integrating the data with knowledge from the mission itself in this notebook form, and then running is a perfect place to do workshops. It's a perfect place to put in undergraduates who are first learning how to use these kind of data, and they can learn it all and run it all on this platform. We've done this as well for JWST. They had a whole bunch of things called JWebinars that ran on a science platform as well, built very similarly. It wasn't as permanent, but it could be put with the data that they were going to use and the notebooks they were going to run, and they could hold a whole workshop for people to run it without having to install any data. So in this way, we're trying to make it easier to give the community the knowledge they need in order to work with the data that is at MAST. And at that, I feel like I've probably filled up my 15 minutes, so I will stop.
Okay, great. Thank you, Susan. So what we'll do is like what we usually do. If you have short clarifying questions, that would be great. And of course, chat is available, but we will switch over to Erik. And then at the end, I hope we can have a fruitful discussion for like both talks together. Okay, wonderful. Okay, so next talk will be, so thank you, Susan. And, I'm looking forward to the discussion. Erik will give us the talk about, well, maybe a little bit on the track of what Susan was just mentioning about how they serve and use Jupyter notebooks at Space Telescope. I'll just say a few words about Erik. So he's a project scientist at the Space Telescope Data Science Mission Office and primary contact for the development of data analysis tools produced by and for Space Telescope missions. He received his PhD at University of California, Irvine. He's interested in dwarf galaxies of the local group in their own right as the probes of nature of dark matter, and interested in applications of modern statistical methods to enable new science, and one of the founding coordinators of the AstroPy project. Okay, wonderful. Erik, take it away.
Fantastic, thanks. My slides are visible right now, right?
Yes, excellent.
Awesome. Fantastic. Yeah, so I want to spend a little bit of time talking today about how we're using Jupyter Notebooks and really Jupyter as a platform, which I'll define what I mean by that in a little bit. So with that, I'll take it away. So I'm going to try not to. I'm going to, coming off of Susan's, I'm not going to spend a lot of time talking about the kind of data we have, but instead talk about a little bit deeper of a dive into how we use notebooks to actually make that data more accessible and usable. So let me start by making sure we're on the same page about what I mean by Jupyter Notebooks and notebooks more broadly. So that can, probably many of you have seen these in some form or another, but I want to make sure we're on the same page of understanding this. So to me, Jupyter Notebooks, they have a definition that you can see on the slide, but to me, there's really like two particularly useful things that they represent for us as either scientists or technical folks supporting science in astronomy. One is that it works as a lab notebook. So my partner's a chemist, and like she's constantly like rolling her eyes at us astronomers for not like having a lab notebook that you have like sitting on your desk and you're like, yeah, I did mix that chemical with that other chemical. And in my mind, Jupyter Notebooks can serve the science community directly in that it's basically can be our lab notebook because it lets us intertwine data and results at the same time. So that's sort of the immediate, the sort of direct thing that I use them for in my own science. But then the second half of it that's more closely tied to what institutional players like Space Telescope or many of us might be thinking about is that it's a way to transmit a sort of scientific story as a single thing, right? Because notebooks allow you to keep code, say equations, visualizations, either separate visualizations or the output of your code itself, along with text, and sort of tell this whole self-packaged story together in literally one file sometimes, but often one web page is what it ends up being in practice. And then the second half of it is it all works in a web browser, which is about the most generic piece of technology. Everybody, you got one that can handle it right here, probably in your pocket. So with that in mind, I'll just show a quick example here of how this plays out. Many of you have probably seen notebooks before, so I won't spend a lot of time on here, but it just shows how, a notebook is code intertwined with sort of narrative information about what that code does and, the outputs of the code and plots and various things like that. So that's the core idea we're talking about when I'm talking about notebooks. Yeah, so those are the sort of practical elements of it. But I also want to highlight, right, a separate item that drives some of the stuff I'm going to talk about technologically, which is that you can take it one step further and not use these just as tools to communicate, but also ways of sort of having long-term replicability or reproducibility. You can ask me later about the difference between replicability and reproducibility, but that's a pedantic discussion. The core point is that these tools, in addition to telling you the story that you might want to transmit, you can use it to store your own story, right? So I'm just giving an example of a paper I wrote several years ago where basically all of the words that describe how you would reproduce it are in a notebook that I publish on GitHub at the same time as the paper. Like people, I'm not the only person to do this these days, certainly not. But the key point is this is another reason to consider notebooks as infrastructure items, is because our user communities will understand how to use them in this mode. And then last, which is what I'm going to emphasize more for the rest of this talk, is that they're more like tools for transferring knowledge from experts to less experts, which in the context of Space Telescope generally means, how to use Space Telescope mission workflows, Space Telescope mission data, that sort of thing. So all of those are applications to notebooks, but I'm going to primarily focus on this particular element for the rest of this talk, although I would be happy to chat about some of the other things during discussion. All right, so with that in mind, let me just show some of the examples of notebooks we have at Space Telescope, and how we present these to users as sort of web pages. So I'm going to start by thinking about missions that are already clearly flying and like very impactful, Hubble and JWST. So I'll start with one example, which is DrizzlePack. So DrizzlePack is a piece of code that that has a long history, 20, 30 years, I think, or something like that, that is really central to a lot of imaging workflows with HST, but it also is sort of, depending on who you ask, at previous versions of it have been infamously difficult to use because there's lots and lots of knobs you can try and play around with. So as part of a sort of hack day project that a group of Space Telescope scientists did, they built a bunch of notebooks that you see the first of here that sort of told the story of how to use, you might use DrizzlePack. So what you're seeing here is basically a screenshot of a web page, because this, I'll put links at the end that'll let you find these, but these are all now put on a web page that you can view as just an ordinary web page. And right now it just looks like text, even though it was originally written as a notebook. But as you go further down, you start seeing that the code is interleaved in it, and it renders just like a notebook does. Even though you don't see it necessarily as a notebook, the code itself was written and tested as part of a notebook development process, and then turned into a website like what I'm showing you a screenshot of right here. And don't worry about any of the details of what this is telling you. The point is to just get across that this is sort of the kind of thing that we often see. Another example is more recent work, and that there's been a much bigger focus on lately, is of course JWST, because it's obviously the big mission lately, and it basically builds on that same kind of experience, right? It has a few extra bells and whistles if you want. So one of the interesting things in particular is that there's this download notebook button in the upper right. And I'll talk more in a minute about how we see that all fitting together with other workflows. But in addition to being this nice clean website like the last one, we're now starting to integrate some of this machinery. This is actually a slightly older version of the rendering, but the key point is there is something like this on the existing machinery, and it helps you more cleanly integrate workflows where people look at the documentation, see it in sort of a clean presentation like this, and then move later to them running the notebook themselves, if they so desire, right? You can also, of course, just take this, learn from it, write your own Python script or whatever you want to do. But one of the things we've been trying to emphasize a little bit more on the JWST side is that you can take these notebooks and turn them into your own workflow, like copy and paste or download the notebook and just rip it apart and do your science with it. And just to illustrate that, right, it goes a lot more down into the weeds, where it does things like shows you how to create a PSF, describes some things about how you might go about doing this. But then I also want to highlight something that I think you will not see in the real notebook right now, which is a note for developers. Right, there's a special rendered version where part of our process is, as people write these notebooks from science teams, they will notice things like, oh, it's kind of annoying to do this. This function didn't work quite the way I thought. Let's tell the development team it would be great if they could update the code to do this other thing. So this is a hidden element of the process, some of which is visible on GitHub when you go and look at the notebooks. I mean, it's all visible on GitHub, but some of which is visible when you visit the rendered web page. And then in some cases, it's not, just to not distract from the flow of the notebook for the science community. But the core point is the development teams now go back and look at those now and again, and are like, oh yeah, we should definitely do that thing the scientist said, because that'll make their life easier, but they haven't had the opportunity to implement it. So in this sense, for JWST, it's not just a communications tool, it's also a way to feed back to the internal development teams how to improve the tools that they're providing and that are being showcased in the notebooks. All right, let's see how we're doing on time. Maybe I'll just briefly talk about this because Susan already talked about it some, but I do want to highlight, there's also notebooks specifically highlighting, MAST in the sense of being about how to do archival science, as opposed to the previous ones, which are more about, science data you've just gotten, or that's your data or very recently taken data. But to highlight the value of this, I think there's this great tweet here that's basically like, I did science in the first day of tests, and I used your Jupyter notebook tutorials to figure out how to do it, right? So like literally within a day, people can take these notebooks, run off and do something significant, publishable with them. And that's part of the value of notebooks, is that that give you some place to start so you don't have to figure it out yourself. Let's see. You know what, we can come back to talking more about the test notebooks, or I mean the MAST notebooks if people are interested, but I just want to make sure we have plenty of time for discussion. So I'm not going to dwell too much on this other than to just give you a quick sense that there's a whole bunch of different areas of notebooks that we could follow and we could talk more about. Oh, right, but one of the key things to point out is that part of what it is about how to get the data from MAST onto a notebook. And this is a key element I'm going to talk about in a moment also, but that it's very important as a now tip for developing notebooks to make sure that stuff is written not in a way that's local to your laptop or your development environment if you're working at an institution, but rather generalizable so that someone in the external community can access the data. All right, so now then the last thing to say about notebooks before I go into a little bit more in how we make sure these notebooks stay stable is to emphasize why, another reason why we're doing this, which is about science platforms, which this crowd certainly is at least somewhat interested in. So what I mean by that is that notebooks are a way to more gently have a transition between more traditional workflows and platform-oriented workflows. So what I'm showing in this slide is the sort of difference between, what I would call a traditional platform where you just do stuff on your laptop or your desktop, depending, and one where you added notebooks, which are not that different. Your notebook is maybe not a paper notebook, it's a physical notebook. And you may be a little bit more limited in the tools available to you just because you have to use something that can render properly a notebook, but that's not very limiting these days. You can do everything up to and including Fortran in a Jupyter notebook. But the reason why this is useful is because when we move on to a more standard, a science platform that's actually run in the cloud, you can essentially use all of the same pieces you're running that you're running in your laptop. You just move them onto the cloud, because almost all cloud tools and science platforms that anybody in astronomy is developing uses this Jupyter platform as their way of doing it. And so it very naturally helps you say, okay, it's really not that different to run my thing on my laptop versus run it in the cloud. It's just that the data are a lot closer to the computer where the notebook is running. And I can move back and forth between these if I feel uncomfortable with, I'm not sure what the platform is doing. But I can transition easily from one to the other. So one of the core points here in my mind is that thinking carefully about designing notebooks is sort of a core element of designing any science platform, because if you don't do it, the scientists will just not, it'll feel too unnatural to them. It's the way to frame it. All right. So then let me just spend a few minutes talking about how the process by which at Space Telescope we're developing these notebooks. So this originally was a very organic process of just like people wrote notebooks and put them places, but we're trying to make this a little bit more replicable and reproducible process so that you can actually have a lot more faith that the notebooks will last in the long term. That's sort of the core goal of this, is make sure it's got decent engineering underpinnings, that it's not just people writing notebooks that work for them on their laptop, but actually something you as the user can assume is going to work if you follow a certain process or follow a certain process to use them. So the core process is still is a sort of standard GitHub workflow. So we have a notebook GitHub repository. For example, for JWST, it's this one called JDAT Notebooks. And you can see here, this is someone internal to Space Telescope on the notebook team who just basically said, oh, I found a problem with one of the notebooks. I've made a pull request to do that. And it's a very standard, typical GitHub workflow to do that part of it. The key difference is notebooks generally do not have as clean of a representation in plain text as, say, code does that you would typically review in a place like GitHub. So we have a few plugins, a few tools that exist from the external world that we use to just make this review process easier, which again, we can talk about details more later if people are interested in discussion about that. But the more complicated part ends up being the sort of internal process and understanding how we make sure everything has gone through a process or has actually been checked by enough people that we believe it might work, 5 years in the future or even 1 year in the future. So the basic process here, hopefully this is big enough you can read, but I'll try to talk through it. Is that somebody creates a notebook, and it's left unsaid in this process how that's done. There's of course lots of management stuff about that, but we don't care for our purposes of this discussion. It could even be random external contributor who's decided they think this notebook would be cool, right? It doesn't even have to be inside the building. They submit a pull request, which triggers 2 different reviews, which after a while we've realized is an important element. These reviews might end up being done by the same person as part of the same GitHub interaction, but it's important to conceptually separate a science review, which is essentially, is the science output accurate and meaningful, and can a regular scientist understand it? And then separately, like, did you follow the style guide? Are we more or less following PEP 8? Are you doing anything really insecure? Like, did you put your credit card number in your notebook? Obviously, most people know not to do that, but security concerns like that. And those are 2 separate reviews that are sometimes done by the same person, depending on their skills, but often are done by 2 different people because they have different areas of expertise. And then once those reviews have been completed, the pull request gets merged into the GitHub repository, which triggers a continuous integration process that turns the notebook into a pretty website and puts that website up somewhere just like I was showing you in the previous few slides. So that's sort of the big picture element here. Then there's a process which maybe I won't dwell on just again for the sake of time, but about how if there's a problem later on, right, the continuous integration runs every week or so. We've been changing, but regularly anyway. And sometimes notebooks stop working because some piece of code somewhere in the whole wide ecosystem broke. And then there's a process that's sort of internal to the institute, but transportable in some ways, for how we then check that if that problem is fixable, fix it, or alternatively say the notebook is clearly not working anymore, so we're going to just put it in a corner that says no longer supported. So both elements are important to think about when designing the process, even though it's really only the first one, the contribution process, that's sort of obvious when you start working on it. All right, so yeah, the next element is to just point out that how the CI process works. There's a notebook infrastructure repository that's separate from the actual content repositories that is shared across an HST repository, a JWST repository. Various other missions are going to get their own, but the infrastructure is all shared between them, and all the CI machinery is sort of implemented in this repository, even though it's used elsewhere. Maybe I can talk more about this if someone wants to ask me questions about some of the technical details. If you see anything on the slide where you're like, oh, I want to ask about that, you can ask in discussion. And instead, I just want to take a minute or 2 to talk about some lessons I think we've learned through developing this infrastructure. So the first one, I think it's very important to know that if you're in a situation like we're in, where the notebooks are very different in the sense of using different observatories or instruments or very different run times, it can lead to a whole bunch of headaches, right? Like there's just a random example of a notebook that was constantly a source of problems for reasons that are not that important, where regularly someone would say everything except the AMI notebook seems to work fine. And so having multiple repos using the same infrastructure is a really helpful thing for that, because it means you can be like, okay, this one is really very different in how it runs, so we have to tweak how it operates, but all the other 50 notebooks are similar enough that we can keep them over here. So that's one lesson I think took us a long time to figure out, but is transferable to other folks. I think another lesson that I really was counterintuitive until we ran into it a bunch of times is that it's really hard to convince people to make their notebook small enough to run on CI, by which I mean, reasonable execution time, because lots of interesting problems people want to document take hours and hours and hours to execute. And you often have to convince them, no, let's pare this down to not all of the data in the archive, but one image. And it turns out you can still demonstrate all that, put a thing at the bottom that says, uncomment this line to get the whole archive. But it'll actually be runnable continuously and regularly deployable if you do that, as opposed to the takes 10 hours to run. We have to have a completely different process. And that seems like a major restriction, but the thing is, it turns out for the use case of notebooks like this, almost always your users are going to want that too, right? They're not going to, most people don't have the patience to download a notebook, run halfway through, see a thing that says, this will now take 10 hours to run, or even 10 minutes to run, honestly. Most people just walk away and don't come back. So using the constraint of, if it's not annoying to run in the CI, it's probably not going to be annoying for a human to run, turns out to be a very valuable checkpoint in the whole design process for the conceptual design process for a notebook. Another thing to keep in mind is that when you're designing the CI like we're doing, we spend a lot of time realizing headaches that come from, we only generate the notebooks that are changed at any given point in which they get changed. We don't continuously every time generate all of the notebooks. That's good for a lot of reasons, but it's a lot more, it ends up making things a lot more complex. So if you're thinking about doing something like that, well, you can use our machinery, of course, but if you don't want to do that, you'll have to spend a lot of time iterating on your design, because it's very hard to get that right without having real practical experience. And then the last point to highlight is dog fooding is important. What I mean by dog fooding is using the same process for your, crack development team as for the random people either in your institution or outside your institution who might be contributing, because it's once you know how the system works, it's very easy to be like, oh, I'll just do this quick step, this big step to make it so that we'll work around the problems. But most people outside of the development team don't know that, so you really need to make sure your team is working in the same process as your external contributors, or else you won't get external contributors, essentially. There's more, but the rest is not actually that critical to show, other than maybe I'll have this little video run to show you how notebooks run in MAST, and maybe I'll just stop right there, and we can start our discussion.
Okay, great. Thank you, Erik. Okay, so let's open it to questions. So please raise your hand or write it in the chat. And while we wait, I wanted to maybe ask if I understand correctly. So your primary goal with notebooks is that you download them, right, and run it on your machine. It's not that you run it on the cluster or somewhere on the Space Telescope. Is that correct?
Right now, that's mainly what we're doing, primarily because we don't have a long-running platform for most. Well, we have the Tyke, which Susan mentioned, but for general, like all of the missions, we don't have something everyone can go for anything.
Right.
So the idea is, right now, the only platform available is your laptop, but there are many efforts both in progress and, for example, that exists like Tyke. And one could imagine, say, a Ruben platform could run some of these things usefully, where there would be buttons added to that download notebook that's also like, launch this notebook in that platform, this platform, the other platform. And the idea is these are all essentially the same. Download the notebook to your laptop is not that different from run it in platform X, where X could be just about any platform because they all use notebooks. And so that's the core idea, is that in my mind, it's almost the same thing. Does that make sense? Right.
I know, because the problem for Ruben, I think many people are thinking is, how do you ensure that something is scalable? And, if you want to run it on many cores, which is a little bit Ruben problem, which is maybe not exactly directly here.
No, it's a good point. I mean, it's also a Roman problem, for example.
Right.
Roman is spending a lot of time designing their infrastructure to address that. So yeah, it's not, I'm being a bit cavalier when I say you could just run any notebook in any platform. That's certainly not true. But the point is, conceptually, you can, within the constraints of whichever platforms actually fit your data.
Okay, Robert, please.
Hi, can you hear me?
Yes.
Okay, thanks. Thank you both, Susan and Erik, for interesting talks. I really enjoyed them. I have a question for you, Erik. You mentioned, and I would like to hear about the kind of plugins and tools and techniques you use maybe to simplify when somebody makes a PR on a notebook, and those things only change like execution time or version of the Python kernel. That these things don't show up as actually diffs in the merge request.
Yeah, that's the one we've been using lately is this one called Review NB or NB Review, something like that. And so that's what we've been using at Space Telescope. We also do some of this stuff in AstroPy, and in AstroPy we've been depending on Google Colab, and both of them, and which has sort of a review process that you can sort of export to GitHub in a way. And both of those have their upsides and their downsides. I think it's the hardest thing about this is that the review tooling is not nearly as clean as it would be if you just, if it's a Python file or a C file or Rust or whatever you prefer. Yeah, I think the tools that exist are fine. I think one of the biggest advantages of Review NB or NB Review, whatever it's called, is that it integrates well with GitHub in that it like treats it acts like a GitHub review. It's not like a separate review that you have to pop into a different space. It integrates the comments and uses GitHub as sort of the back end, but it's still a little clunky. And I don't, that answer changes every year or so. So probably ask me again in a year and I might give you a different answer, but right now my impression is it's still a little bit clunky, but not so clunky that it's not worth doing, which is actually kind of how it was about 5 years ago.
Yeah, I agree. Thank you.
Susan, I was, for instance, interested, you were showing this time series, notebooks, if I understand, and then how you can get from tests. It was like a light curve was implemented like inside somehow, right? So the user would ask, how does that work? User says, I want this object, and you pull light curve somewhere from somehow below. Like, how does that work?
Yeah, there's layers and layers
right
in that particular item. Right. And MAST was primarily involved in making the test cut features that you were talking about. So as I was talking about, you allow people to get just the pixels they're looking for from this large stack of time series images. And so it's a service we provide that we've wrapped with AstroQuery, which Erik mentioned, so that you can do then like a cone search against the FFI, say, do you have data for this particular star from the test FFIs? And it returns yes. And then says, can you make me a 10 by 10 cutout? And it returns that. There's a very popular tool called Light Curve with a K that was developed for Kepler. And that team, it was primarily developed out of the Kepler guest observer office, and now has been adopted by the TESS guest investigator office. And they then have wrapped AstroQuery essentially to make it have a happy user interface that works well with their time series objects and returns it straight into your Jupyter notebook. So from your Jupyter notebook, you just type, hey, can I get a cutout for this star? And then it says yes. And you go, all right, I'd like sector 5. And sector 5 being one of those 1 month chunks from TESS. And then it'll return straight into, a light curve or a time series object into your Jupyter notebook. And so as a result, people are using the archive very differently because it's just integrated as part of their process. Instead of the first step is download the data, second step, go work with the data. Now it's like you start with the notebook and you say, oh, well, the first step is to get the data, but that's all in this flow. Now I want to change the target. So now I have the same flow and there's no initial outside of this notebook kind of thing. So it's just part of that whole notebook, get the data and then start doing analysis. It's a nice way to work, I have to say, when you can get it streamlined like that.
Can I ask a follow-up about that?
Sure.
So I was amazed by the volume of data. I don't know why I was amazed, but I was amazed by the volume of data going out of MAST. And so maybe this answers my question ahead of time, but there's a lot of discussion still about cutout services for LSST. And I was just looking at the test cutout slide that you were showing, and I'm guessing that there aren't limits. I'm just curious, are you able to let people cut out as much as they want and as often as they want? I mean, I'm guessing that's the case based on the huge amount of data it's putting out. I see you nodding your head. And then the other question I have is just how long does it take to do that?
Yeah, essentially we let people do it without limits. If somebody suddenly parallelizes a huge process and then pings us from 1,000 directions, we tend to notice that and then ask them to stop. So that tends to be how we operate. We have been able to kind of open up how much people can ping us with test cut because we're now operating that service out of the cloud. And so less of it comes through the Baltimore premises. It's going through Amazon servers instead. But this is a very new change, but has speed up the rate at which people can get test cutouts. But it's also great because it means if they just go and work in that time series platform I mentioned, Tyke, they can just do it all in the cloud and it never has to leave the AWS cloud.
Wow, that's awesome. That's a great lessons for us to learn at LSST for sure.
Right. It sounds very much like something that Ruby Science platform would like to do on some level. Yes.
Yeah, putting the services that are very data heavy in the cloud is, I think, a real nice advantage of working in that way, especially if they need to scale up and down a lot.
Wonderful. Okay, thank you. Do we have more questions from the audience?
I suppose Jeff could bring up this topic we're chatting about in the chat.
Right. Well, Melissa raised her hand, so maybe Melissa, and then we can go back to this Jeff. Yeah, Melissa, please.
Yeah, sure. I'm curious if you have Erik, an elevator pitch 1-minute version of the difference between replicability versus reproducibility. I was piqued by that.
Oh yeah. So the short version is the using the definitions I follow, and we'll get to that in a second. Replicability is I can take, you provide your code with your paper, I can run your code and get your plots out. And there's no secret magic sauce on that isn't part of the publication process that lets the plots be reproduced given the input data. Whereas reproducibility is I need to build my own telescope and take the data and see if I get the same science result as you got, but without using any of the same original data. That's sort of in astronomy that, I maybe exaggerate with build your own telescope, but the idea is get the data independently, following my own process separate from your process, but using what you've written in your paper. That's the distinction between the two. Now, my caveat of the definition I use is that there's this great paper that's in the computer science literature, essentially, that's about specifically which one is reproducibility and which is replicability. And it traces like 20 years of papers on this topic, where it's very clear nobody, like about half of papers on this topic choose one convention and the other half use the other. Everybody agrees these are two different things and we have to make a clear distinction between them. Nobody can agree on which word means which thing. So they're two different things, but the definition I gave you is apparently in the camp that's more aligned with the ACM, the Association of Computing Machinery, the like computer science AAS, you might say, whereas the other definition is favored by the national academies. So I don't know, but the key point is those two things are very different, even if we can't agree on what words to use to describe them. Does that make sense?
Yeah, thank you.
Cool.
Okay, so maybe Jeff, you were just pointing out, right, that GitHub very recently had a new feature, right, with the notebooks.
Yeah, there's sort of a feature preview that I think just went live last week, something of a notebook diff tool, and maybe I can phrase this in the form of a question to Erik and Susan that I guess what are the advantages of using Review and B over trying to do things all within GitHub?
Yeah, I would say the primary advantage is that thing that you just put there didn't exist until a week ago. If it existed 3 years ago, definitely would have used that. Although the one key point that I think I'm not sure about, right? So I just learned about this from Jeff in the chat 5 minutes ago or whatever. So I have not had a chance to explore it very much. But based on my like 30-second glance at the blog post about it, I'm not sure it currently supports leaving comments inline, which is critically important for this review process. The review process really, you need to be able to say like, this line of code, you need to change the E to a T, I don't know, or whatever. And like, that's really critical to the review process. It's very hard to do it's just annoying to be like, on line 645, you do this. So the inline review is absolutely a critical feature that Review NB does well. That's why we're using Review NB primarily, is because it does that really well. And if the GitHub one shows diffs but doesn't let you do inline comments, it still is not there. But I'm sure they're thinking about it, right? So as soon as they actually have something that works that's integrated with GitHub, I don't see any reason why you'd use Review NB. I'm sure whoever made Review NB is quaking in their boots right now, unless they were recently bought by GitHub and that's why this happened.
So Erik, so CK is just asking, do you have a link to the reference? That's probably reference to
the reproduce or the replicability,
Right.
whatever. Yeah,
Right.
Let's see. Where I have a link somewhere. I'm
Right.
not sure I can find it in the next 3 minutes.
If you don't find it, I think if you drop it in the Slack channel, that would be the best location. The
Gotcha.
LINCC Tech Talk Slack channel.
Yep.
Okay. Do we have maybe any last minute questions as it's 10:50? Yeah, Knut, please.
Sure. Thanks both for the great talks. And just on the subject of reproducibility and replication, I mean, one sense in which it makes a difference is does Rubin, for instance, need to preserve every data release going back to DR1 for all of time in order to allow results to be checked and verified? And I think with your definition of replication, I think the answer is no, right? I mean, most people don't care about that. What they care about is getting the qualitatively same result, maybe with updated data releases or new software libraries that do the same thing as the old ones but aren't identical.
Yeah, I mean, this is a question that we will not answer here, but it's a great point, right? I think my instinct is that papers really should be replicable, because there's so many stories that I could bore you with about times when someone wrote a paper and they got their result, and then somebody else tried to replicate it in the sense of like make exactly the same plot with the exact same input, and they couldn't. And then, they go and talk to someone, and half the time they're like, I give up, can't do it, moving on. And then half the time there's like a story, they went and like did extra work, found the code, and it turns out there was like a bug in it, right? And like some major science result was wrong, not because the idea written down in the paper was wrong, but because the implementation was incorrect, because it's so easy to do that, right? And then the other half of it is often in the modern era, so much of the results we get are sort of dependent on information that you don't necessarily write down, right? Like the seed for your random number generator can sometimes be a very important element in understanding the results you get. And there's no way we don't have a culture around writing that, and we shouldn't, I think, in our like narrative papers, but we should have a culture around, here is my notebook or my script or my whatever, here's what you could use to get out the answer. And that way somebody can actually go and look and see like, oh, the reason why you have a different answer is because or why I got a different answer than you is because there's actually very strong sensitivity to the random number generator seed or whatever.
Right, and that would be an important result to discover, because if you have a result that depends on that, it's not a result worth publishing.
Yeah, but I think the literature has papers written that way where they just didn't know, right? People make honest mistakes all the time, and science is about being able to collegially exchange information about this. Now, the distinction I was going to make is that's about papers. You mentioned data releases. I'm actually less sure that's important. I think you have a very good point. Maybe that's not as important for data releases, only because there's a whole bunch of edifices surrounding that aren't necessarily intended to, if there's going to be another data release, it's very different from a paper that's supposed to stand on its own until the end of time. So I don't know if that rule I was describing really applies to institutional players in quite the same way as it does to papers. I haven't really thought that hard about it, but I I'm open to that.
Yeah, it's a very strong cost driver. Yeah, if you had to keep them all. Yeah.
Yeah, I mean, I can say from MAST perspective, we in general don't encourage keeping old data releases after reprocessing happens because it just becomes explosively expensive, right, to keep everything around. But if there is a science driver for it, then of course we listen to those arguments. But in general, we've never had people come back and ask us for data release 1 from Kepler.
Okay, great. I see, Erik, you posted a link in the chat, so grab that before we close.
Yeah, and I love the title says it all, right? The title is Reproducibility versus Replicability, a brief history of a confused terminology. The fact that someone bothered to write a paper with that title shows how much of a disaster that literature is. I mean, the terminology in the literature.
Okay, wonderful. Thank you all for nice discussion. Thank you, Erik and Susan, for coming and giving us a talk. We'll have the next talk. It'll be April 13. Drew Oldak, who is one of our software engineers, will show his GitHub repository, which enables you to start new projects very efficiently and nicely. It's very neat. It's very neat. So I hope you will join us doing our next talk, April 13th. Okay, thank you all. See you next month.
Thanks. See you later.